Hello everyone, I am Manogna. I will be presenting our work pSTarC pseudo source guided target clustering for fully test time adaptation. Suppose we have a CNN trained on driving data collected and in clear weather conditions. We know that during test time it can encounter other weather conditions like rainy, snowy, nighttime, and so on. So this is an example of a real world domain shift. Another example is if we have trained a model on real data and we want to evaluate them on say clip art, painting, and sketch images. So this is another kind of domain shift. So deep neural networks tend to perform poorly when it encounters such distribution shifts. So it is increasingly important to equip these models with online adaptation capability so that they continue to retain their performance even on encountering such domain shifts. Under the head of domain adaptation, these are the four main topics explored: unsupervised domain adaptation, source-free domain adaptation, and more recently test time adaptation and continuous test time adaptation. In this work, we focus on test time adaptation and its continuous version as well. To formally define in test time adaptation, given an off-the-shelf model, the goal is to minimize a test time objective using a batch of samples xt which arrive in an online manner from a domain different from that of training data. So in test time adaptation, we deal with actually a single domain shift, but in continuous test time adaptation, the test samples can come from domains that change with time, as shown here. So our method is inspired by the success in source-free domain adaptation techniques. Well, to highlight the difference between SFDA and TTA, SFDA methods leverage abundant target domain samples and also employ clustering objectives. In this paper called Attracting and Dispersing, they propose to enforce consistency between a sample and its neighborhood predictions while also maintaining diversity in its predictions. However, in TTM methods, the classifier is usually kept fixed in order to preserve discriminative information, and objectives like entropy minimization are used to update a small number of network parameters. Here we question if we can employ SFDA techniques for test time adaptation, although we do not have access to a lot of samples at a time. With the goal of mitigating this discrepancy between these two problems in terms of the objective function and the amount of data available, we propose this method pSTarC pseudo source guided target clustering. So the first step here is pseudo source feature generation. So as the source classifier defines the decision boundaries and is usually kept fixed during test time adaptation process, we question if we can leverage this to synthesize pseudo source features. This is a simple one-time process, and the generated features can be stored and be used throughout the adaptation process. The next step is the pseudo source guided target clustering, where we use the generated features to effectively cluster the test data, and we also enforce a consistency loss between a sample and its augmentation. So in order to generate pseudo source features, we first randomly initialize a feature bank of size n, which is set this way. Here C is the number of classes and NC is the number of features per class we aim to generate. So we optimize this feature bank using entropy minimization and diversity maximization loss. So the entropy minimization loss aims to cluster the samples, while the diversity loss aims to maximize the entropy of the class distribution. So this is to prevent the trivial solution of all the features belonging to the same class and generate approximately equal number of features per class. This is a TSNE plot of the generated source features, where there are 12 classes and we aim to generate 20 samples per class for the Vista dataset. You can see that all these are well clustered and separated, but they are the synthesized samples, and we can perfectly label these generated samples using the classifier. The next step is pseudo source guided target clustering, which is done during adaptation. The stars here represent the generated pseudo source samples, and now given the test batch, so all the yellow points correspond to test samples. So given the batch of test samples, we first identify whether they are low entropy samples or high entropy samples. These dark regions define the low entropy region for each class, and the lighter ones correspond to high entropy regions for each class. So for the samples that have low entropy, we define the positives to be the pseudo source samples belonging to the same class it gets predicted into. For high entropy samples, we define the sample only as its positive. That is, we self-anchor the sample. The threshold for determining low and high entropy samples is set automatically for each batch as the mean entropy of the batch. The pSTarC objective which we propose is we enforce consistency between a sample and its augmentations prediction, a sample and its positive, which is either the pseudo source samples or or self-anchored prediction, and we enforce the dispersion loss. So this loss is to prevent the trivial solution of all samples collapsing to the same cluster and ensuring that they are distributed across classes. To summarize, suppose the source model is trained on such synthetic data. Using this, the first step is we keep the classifier fixed and update a randomly initialized feature bank with entropy minimization and diversity maximization loss. Now, given these pseudo source features and a batch of test data that arrive in an online manner, we update the feature extractor while keeping the classifier fixed using the pSTarC objective which we just defined. Coming to the results, we perform experiments on both TTA and CTTA setting on different benchmarks like CFAR 100C, DomainNet 126, Vista dataset, and Office Home. So we see that compared to all the prior methods, that's the source, tint, ADA contrast, which are prior TTA methods, pSTarC consistently either does better or at least at par with the prior methods. We then perform ablation study to understand the importance of each loss component. On both Vista and DomainNet, we see that each of the loss has a role to play, and then we get the best results when all three loss components are used as shown here. We also study the performance of our method for varying batch sizes starting from 8 to 128, and we see that pSTarC consistently outperforms ADA contrast in all the batch sizes. To conclude, we propose a simple and effective framework named pSTarC for test time adaptation. Here we leverage the fixed source train classifier to first generate pseudo source samples. These act like a proxy for labeled source training data and can be effectively used to cluster test samples. Extensive experiments in both TTA and CTTA setting across several benchmarks justify the effectiveness of our method. So, thank you everyone. Please scan this QR code to check out our project site and for the code.